Okay, Assalamualaikum and hi guys. So we back to chapter 1, but we continue on part 6. Okay, so today I will talk on how to derive a rate law that involves early radial mechanism. Previously, we have discussed on those reactions without the early radial mechanism. Okay, so this time is with early radial mechanism. Okay, for example, okay, this example is in your textbook, page 688. Okay, so we have this toluene plus hydrogen to produce benzene and also methane. Okay, so how are we going to derive a rate law for this kind of reaction? Okay, using solid catalyst. Okay, so the first step that we need to do is select a mechanism. Okay, so this is the algorithm lah. So when we select a mechanism, so we have to have adsorption, surface reaction, and desorption. Okay, so for adsorption part, this is similar with those non-irradial mechanism. Okay, so for adsorption, so the overall the rate for adsorption is Ka. So since toluene is in a gas phase, so this one would be pressure on toluene. So S again is Cv. Okay, so when it adsorb on the catalyst surface, it will become T dot S. So that's why Ct dot S over the capital Kt, right? This is small Ka. So this is the adsorption constant, right? And then if we want to describe in a diagram, so this is what it looks like when T is adsorbed on the catalyst surface. So when we go to the surface reaction step, so this hydrogen or this one, okay, will make bonding with T. Okay, so it will not adsorb on the catalyst surface, but it will make bond, okay, between hydrogen and toluene. So it will become benzene attached to the surface plus methane gas. So when we derive the rate law for surface reaction step, it is Ks. Okay, you look here, the hydrogen is in a gas phase, that's why it's PH2. So and then T dot S is Ct dot S. So Cb dot S. Pm, because methane is in the gas phase, right? If it is in liquid phase, so it's Cm lah, over K, capital Ks. Okay, if you look here, what we call it early radial mechanism is this part. Okay, it didn't attach the molecule didn't attach to the or adsorb on the catalyst surface, but it make bond with the reactant. Right, so for desorption, okay, this is how desorption will be look like. So for the surface reaction, if we describe it with a diagram, it will be something like this. Okay, so T making bond with hydrogen and then produce B and methane, but methane also is not attaching on the catalyst surface, right? So here, that's why no longer M remain in the reaction, because methane is already being dissolved during the surface reaction. Not actually dissolved. It didn't. The methane just now didn't attach to the catalyst surface. It's only the bond is is being cut here. Alright. So that's why it's only B dot S. So the overall reaction for desorption is Kd. Okay, K for desorption, Cb dot S, okay, and then Kb, Pb, okay. So Pb because benzene is in gas phase, plus and then Cv, right? So this is the mechanism. So the next step is, okay, we need to assume a rate limiting step. So for this chapter, I always tell you that we need to assume the surface reaction is the slowest step. Okay, so when the surface reaction is slowest step, it is surface reaction becoming a rate limiting step. So if you look earlier, so this is surface reaction step, so we select, okay, we select this step. Okay, so that's why, okay, we're having this thing, this equation. Okay, and then we need to solve for the okay, we need to solve for this constant. Okay, so ct dot s, cb dot s, we need to solve it. How are we going to solve it? That's why the third step, find the expression for concentration of the adsorbed species CIS. So when surface reaction is the limiting step, okay, so the adsorption and desorption will become rapid. So when it is rapid, your Ka, okay, is high. So something over something high, it will near to 0. Same goes by Kd. Okay, so when RAD over Ka equals to 0 and Rd over Kd is equals to 0, okay, so you look back to the previous slide. Okay, so when this part is equals to 0, so it will become CVPT equals to CT dot S. That's why it becomes like this. Okay, so you will have one equation for CT dot S, another equation is CB dot S. Okay, for the fourth step, okay, we do the site balance. Okay, site balance is the total concentration of the active site equals to CV, the vacant site, plus, because you have a reactant T, toluene, and also benzene. Okay, so although the reaction is what? T plus hydrogen, you get alright, you get benzene plus methane. Okay, so we only focus on this one because it is, we assume it is elite radial. That's why this thing is, that's why your site balance having the equation like this. Okay, there's no M and also hydrogen will not involve in the site balance because they didn't occupy the active site. Okay, so by rearranging the CV, it becomes CV equals to CT. Okay, this one is you're going to plug or insert it into this part. Okay, this part is actually for, okay, because you need to, you need to, it is like a mathematic. You need to solve the equation. Alright, so in the end, when you insert CV into the CTS and CBS equation, and then you again all those variable, okay, in this equation, okay, will come out becoming the rate law. Okay, so the fifth step is derive the rate law. That's why, okay, so when you already insert all those equation, this equation, okay, this equation, and also the CV, and then you put in to the RS, the overall rate of reaction. That's why you will get the rate of reaction for toluene is actually this one. Okay, and then you want to simplify the equation. Okay, so that's why it was written here, all this value is equals to K. So you simplify your equation becoming K, okay, pH2, right? So is it actually being simplified into this? Okay, so you can check back your book in page starting from page 688 to 692. Okay, right. So for the next slide is, okay, synthesizing a rate law for reactor design. So this is how you want to design a reactor. So when you have already, okay, obtain data from laboratory reactors, if you look into your textbook, okay, in page 689. Okay, so there are table 10.6, that is a ration data. Okay, so if let's say just now we already produced this kind of equation, try to fit in the numbers like the pressure hydrogen, the pressure of toluene, benzene and methane into this equation. So does it get the same value in the table? If it's get, meaning your reaction rate fit the data. Okay, so this is what actually the diagram is all about. Okay, then when you have synthesized the rate law from data, okay, and then you go to the reactor design. Okay. Okay, so heterogeneous data analysis for reactor design. So step involved, okay, of course, the first one you need to develop a rate law. Okay, find a mechanism and rate limiting step as what we did just now, and then analyze the rate law whether it fit the data. If you have data lah, if not, you only stop until here lah, until you find a rate law. Okay, and then you use the rate law to design the catalytic reactor to achieve desired X. Okay, so sometimes given the conversion of 90%, so what is the volume or the weight of catalyst of the reactor, right? So for the design equation, we use you still have to use your basic knowledge in your CRE1. So this is the batch reactor. So if you look at this thing, so you will substitute your V with W. So your RA will become RA single prime. Okay. So in the end, you will get not volume of reactor, is actually weight of catalyst. Similar goes by CSTR. So last time it was V. Okay, but this time around is negative RA with finding W. Same goes for PBR. Okay, so for example 10.3, okay, if you look here, okay, the molar feed rate of toluene to the reactor is 50 mole per minute. So this is FA naught. Okay, so at this P, at this temperature, okay, this is the mole fraction. And then you have pressure drop parameter, and they want you to determine the catalyst weight in A CSTR with bulk density. This is your rho B. Okay, so again, this is toluene plus hydrogen plus benzene. You get benzene and methane, right? So I need you to to go back and have a look on this one. This is actually your knowledge during reaction 1. So this is the rate law that you derived previously. Okay, so you will use this rate law. Okay, then the only difference is, right, okay, so right, so you just proceed with the pressure and temperature and all the stuff, and then in the end you will get your W is equals to 10,197 kilogram. Okay, so this one is actually example 10.3 in your book. Okay, so I think maybe later I will show you some example that you may use. Okay, you may use this rate law. Okay, this rate law, how to use this rate law in order to calculate your catalyst weight. So normally what we did is when we wanted to find, let's say you wanted to use this equation, right? If you wanted to use this equation, so this one will be used in this equation. All right, so how you want to simplify it? So there will be some statement telling that the constant, equilibrium constant for benzene and toluene is very small. So this one might go to 0. Okay, so it remains RT equals to Kp hydrogen and P toluene. Okay, then you can simplify and use the equation. So I think that's all for now. Thank you. See you next slide.